The last week we did RAG. For some reason I think the program didn't go through, but it has been corrected now. So today what we'll do is we'll do the other technique. Which is the other technique? Fine tuning. So I'll just summarize the technique first, then I'll walk you through code and let's see how much we are able to accomplish. There will be a slightly more tough quiz at the end after we are done. We cannot give you the cluster for so many people for fine tuning together. So depending on your project where you need fine tuning, we will have to make the cluster available on a register booking basis so that you can use it. But it is not possible to give it in a class, for a class, because it will crowd the cluster and maybe crash it. This is the second technique of making money from LLMs. The first technique we talked about last class. That was the RAG technique. I'll just summarize what RAG was. The retrieval based augmented generation or retrieval augmented generation. What was the basic point behind it? There is, the LLM is trained on a corpus of data, which is a general corpus. Now different corporates may have their own corpus, which is specific to that particular organization. Now the general LLM anybody can use, pay $20 and use the LLM. This specific LLMs, which are meant to be used within a corporate or within a well-defined organization, are where the world seems to be moving. So if you use RAG, what do we do? Suppose there are some 50 documents or 500 documents which this corporate needs besides the standard LLM. It is expected to take those documents, convert them into tokens, convert them into vector databases, store them in a VDB, which could be FAS, could be Pinecone, could be any other kind of vector store. And when a query is created, the query first is obviously encoded, then it is indexed into the into the vector database. The vector database identifies a bunch of documents which may be in close proximity to the query. So the bunch of documents along with the query is taken and then given to the LLM to produce an answer. So that is how RAG works. So in essence, RAG is where the excess information is treated not intrinsic to the LLM, but is treated as if it is some kind of an extra or an appendage to the LLM. It is not absorbed by the LLM. Now, on what kind of situations would you use RAG and on what kind of situations would you look at fine tuning? I would use RAG if the size of the extra information that I am going to incorporate is limited. Then I can hold that extra information in a vector database and then use that information. When that kind of limitation is there, that limitation can be, let's say 500 documents or a 1000-page document, which is that extra information, but it is kind of upper bounded. But on the contrary, if an organization has information which is of a very large area, large domain, and which will probably stay for a longer time, which will not change, in those situations we would use fine tuning. Fine tuning is also recommended when the information is not readily available or should not be readily available. It's a property of a corporate and the corporate would rather absorb it and then give an LLM rather than give it externally. So that is another area where LLM can be used. The other thing about which is very important, which RAG may not have and an LLM will have, is the amount of security for the information. See, RAG is an external information, could be corrupted, could be poisoned, could be biased, could be anything. Whereas an LLM information, because it's trained one time and it's intrinsic to the LLM, can be made more secure, may suffer from less of training poisoning, data poisoning, all this. Now, the basic challenge of an LLM is how do you train it on limited resources? How do you fine tune it? Obviously on limited resources. Now, in order to understand fine tuning, let me talk a little bit about this problem of fine tuning. Why do organizations not do fine tuning? I think to a large extent we discussed it in the last class, but I'll just harp on it a little more. The first problem of fine tuning is we are dealing with a large set of parameters. A typical LLM of any proportion today, of any utility today, will consist of how many parameters? We said 70 billion parameters, or nearby that. It's very difficult for 70 billion parameters to be trained again and again, which is what a fine-tuned LLM will expect you to do. So the effort taken or needed, both in terms of compute power and the duration, is pretty substantial because of the large number of parameters involved, in especially today's LLMs. So that is the final first deterrent. The second deterrent obviously is related to the first, is what kind of compute power do you need? Because training an LLM, immediately when people talk about fine tuning, the immediate thought that comes to people's mind is what? Training is a big activity. Is fine tuning also going to be similar activity? Because in typical training we know the time. It takes 6 months, it takes 2100 GPUs, 800 GPUs to train. Nobody has that kind of resource, and nobody has that kind of time, and nobody has that kind of bill for energy. The amount of energy it's going to consume is pretty high. As you are aware, NVIDIA's current thrust or investment is not so much on chip side, it is also on energy side, because they are realizing these chips take a lot of energy and you have to invest so much energy. That's the second barrier for fine tuning. So first is obviously the amount of time taken to retrain, and whether we'll be able to pay for it, whether we'll be able to cost fine tuning. I will also share this. If we take our A100, just one single A100, and try to use it for fine tuning, it will take a lot of time to use it for any sensible task. On the contrary, the cluster which is used for Tantric, which is a 15 node cluster, each with a single GPU, now that seems to be far more powerful and could be utilized for fine tuning. And our today's case study, our example, is based on utilizing the Tantric cluster, which is those 15 machines each with a single GPU. How can you employ that in a fine tuning loop? Now the next question which will come is, so do I need 15 machines when I want to do fine tuning? Well, technically yes, you require a substantial amount of compute power, but whether it's 15 machines or 20 machines or 30 machines, that depends on you, in the sense how much time you have and how complex is your fine tuning job. So there is no hard and fast rule that I have seen that it takes this long or it will cost this long. Now, which is a more elegant technique given RAG and given fine tuning? What do you think? When I say elegant, I say more packaged, more easier to deliver. You will say RAG? Well, I will say fine tuning, because you are just delivering one solution. RAG means you are delivering the solution and you have to deliver a whole bunch of documents or the vector database, whatever. So from a neatness perspective or from the concise perspective, I just deliver this LLM. Let's say LLM for Apollo hospitals, LLM for Cisco, which is trained on all Cisco products. Apollo hospital LLM, which is trained on the medicines, the various faculties, the various labs which Apollo has, and gives a lot of details about that. So that is an LLM which would be ideally fine tuned, because that information is not going to change so often. Every day a new Apollo faculty is not getting added. Every time a new lab is not getting added. Same thing with Cisco. Every day a new product is not getting created. So situations like this warrant a creation of a LLM which is fine-tuned. So now I'll talk about the fine-tuning process and we will show you how fine-tuning happens. No, I think I'll use the open board for it. See, there is something very conceptual that you need to understand about fine-tuning. When you understand it, you are done. So let me try and give you the concept first. It's very simple concept. In order to understand the concept of fine-tuning, let's just trace back a little to the concept of a regular ANN or a deep neural network. Let's just walk through that process for 5 minutes and then I'll elaborate how fine-tuning is different. Okay? Let's look at the regular training for 5 minutes. How does regular training start? You start with an input, let's call it X. That input you subject to a combination of linearity and non-linearity. If you want linear, you say Wx plus B, and when you have to apply non-linearity, you say some ReLU, GeLU, whatever. So basically by applying linearities and non-linearities together, you take an X and pass it through thousands of layers and you get a Y prediction. Then what do? You take the Y prediction and compare it with Y and you create what is called as a loss function. You create the loss function. Having created the loss function, what do? Then you start the back propagation, and what happens during back propagation? So you have dou L by dou Y pred, then you have dou L by dou W at the outer level, then keep going back using chain rule, and what happens? At the end of back propagation, what do you have with you? You have essentially at the end of back propagation, but before applying the weight change, what do you have? You have all the derivatives or so-called gradients. You have all dou L by dou W's, where L is the loss and W is each of the weights. So this is not such a simple task, especially when you are dealing with 70 billion parameters. You have at the end of the back propagation flow 70 billion gradients. Do you agree? Yes? At the end of back propagation, you will have 70 billion gradients with you. 70 dou L by dou W, one for each weight. Correct? Is this point clear? You will have 70 billion gradients. I am taking 70 billion as a number. A lot of gradients, a ton of gradients. Now what do? You take this gradient and as dictated by your optimizer, you take your gradient and then use it to alter the weight. What do you say? W new is equal to W old minus alpha times the gradient. Now this is a very simplistic view. Life doesn't go with this way. This is the stochastic gradient, right? Normally we never use the stochastic gradient. What do we use? We use the Adam optimizer. So what's so special about Adam optimizer? Yeah. Now, what is the equation for Adam optimizer? Okay, the Adam optimizer, you just did the quiz. Adam optimizer has two moments. One is called the moment of, there is momentum and there is learning rate decadence. No? Okay, let me elaborate on this. See, nobody uses W new is equal to W old minus alpha times the gradient. Nobody uses this. This is only for textbook. The least practical thing of this is Adam or wide Adam, whatever. So if you think about Adam, what does it do? It says that the update to the weight which I carry out should not be just the current gradient. It should take into consideration the history of the gradients of this weight. That means the current gradient or the current application should not be just dou L by dou W. It should have dou L by dou W, which is the current gradient of loss with respect to weight, but it also should pay respect to what are the previous dou L by dou W's with respect to the same weight, same parameter. That is called momentum. Just like, so far the gradients have moving forward, they can't suddenly move back. Or if they decide to move back, the backlash of the previous gradients should have a dampening effect on the current gradient. It should not be wild. So how do you ensure gradients are not wild? You ensure gradients are not wild by applying a momentum term to the earlier gradients. So you have to keep track of the earlier gradients. And then using the earlier gradients, you compute the new gradient or you use an equation to take the impact of the previous gradients and capture that in some kind of a variable. And then use that variable to change the current weight. So it will not be W new is equal to W old minus alpha, that will be there, but this dou L by dou W, that gradient that you are using, also will have a momentum of the previous gradients into consideration. So all that will be used. That is one factor. What else does Adam do? There is one more thing which Adam does. Yes. Excellent. There is another thing which the Adam optimizer does, which is changes the learning rate. It decays the learning rate. It says initially I am using a certain learning rate. As the model gets trained more and more, I shouldn't be using the same learning rate. I should be using a decayed learning rate. So the decay of the learning rate also has to be factored. That is called the second moment. So for that there is a parameter. For the first moment there is beta 1. For the second moment there is beta 2. Why I am saying this is, for every weight there is a beta 1 which keeps track of the momentum and beta 2 which keeps track of the learning rate decay, how the learning rate should be decayed from one epoch to the next epoch to the next epoch. So if you keep these two things in mind, there is a lot going on in just the weight update. See, we take this weight update as a very trivial operation. We just are used to thinking of it as W new is equal to W old minus alpha dou L by dou W. It's not as trivial, as simple as that. First of all, there is a huge amount of time spent in computing these 70 billion gradients, and it's not these gradients alone, but if you are using a sophisticated optimizer, you will have the beta 1s and the beta 2s which will change or which will be different for each weight parameter or each parameter. So all these will have to be kept in mind before applying the change to W new. Okay, now just keep this in mind. We will have to revisit this entire back propagation computation of the new weight a little when we do fine tuning, but the process will remain the same. The reason I highlighted this is this process undergoes a bit of change or undergoes a substantial change, I would say, when you do fine tuning as against first training. In basic training only this much happens, that these parameters keep changing, and because these parameters are keep changing and there are so many of them, it takes that long. But in fine tuning what happens and how does it happen? Okay, now let's move on to the, acha, is everybody clear? Especially, acha, another thing, now you guys should know all the optimizers and how they work. You should not depend on writing Adam and be done with it. You should know it intimately. You know how to write an Adam code, how to write RMS prop. You should be able to write that by hand, because a lot of people in AI interviews are very particular. Does this person know this intimately, or is he just a superficial guy who picked up Python code, patched it together and did it? Which we are trying to avoid by giving you the tantric story. Now, let's go a little further. We'll talk about fine tuning. Now, fine tuning has been done on three kinds of architectures. There are three basic modes of fine tuning. After that, fine tuning has been changed dramatically also, but at the core, fine tuning as a science, you have to understand three different ways. First way is, which is done if I just have an A100 and I want to do fine tuning, what will I do and how will I do? Okay, just think with me a little. Achha, this session is going to be a little deep, so if there is any memory or your CPU is not all right, either you go home or go to sleep. Okay, so you will need to be alert and listen quite carefully because there is deeper concepts involved. Okay, so the first model is if I have an A100, how will I do fine tuning? Very simple. When I have an A100, how many GPUs do I have? 4. A typical A100, it may vary, but by and large, most A100s in the world will have 4 GPUs. Each GPU will have a certain amount of main memory, certain amount of GPU memory as we call it. Now, in this case, how the fine tuning structure, the process structure, how will it look? Let me just describe. Here the process structure will be very simple. What will I do? I'll run 4 processes. First I'll create 4 processes. I'll create means who will create? Fortunately, the framework which we use today, PyTorch, automatically will allow you to create a process group consisting of 4 processes. So you will have 4 processes, one running on each GPU. Each process will be given one CUDA GPU and it will run on that. Now, each process what it will do? So each process will have this whole model will run on each process. Whole model means all the layers of the model will run on every process. The training will or fine tuning will be done on every process. Second, the data will be split. So suppose there is, assume for the fine tuning process I am using 100 GB of data. Let's assume 100 GB of data. So I will have to slice it into 4 equal slices, 25 GB each, very reminiscent of how Hadoop kind of architectures work. Those of you remember Hadoop or have done Hadoop. So 25 GB will run on every GPU on every process. Each process will use its 25 GPU and train. Now it's not as trivial as that, but the basic process architecture will be the same, that 4 GPUs, 4 processes, each having 25 GB, same model. The model will be the same. This is one architecture. I am going to go deep into this architecture, hold. I mean, once I cover everything, I will come back. This is one model, process architecture. Is this process architecture clear in your mind? This will need a classic A100 kind of machine where you have potentially more powerful GPUs and each process is running with separate pieces of data. Okay. One shape. Second model, second way is what we are going to learn today, which is called DDP, Distributed Data Parallel. This model which I just described is called data parallel, just data parallel. The next model which we are going to talk today is distributed data parallel. What is distributed data parallel? Well, just extrapolate this idea. Instead of one machine with a certain number of GPUs, I will have n machines, each with one GPU or one more than one GPU. Are you with me? No, yes. That is called distributed data parallel. So it is the same thing as data parallel where data is cut, but only difference is the processes which are part of this DDP are not sitting all on one machine, they are distributed across multiple machines. Now on each machine, what will be there? Suppose that machine has 4 GPUs, the first machine has 4 GPUs, there will be 4 processes running. The second machine has only 2 GPUs. How many processes will run? 2. And so on. Now in our cluster, each of our machines has only 1 GPU. So how many processes will run? 15. Each with a separate GPU. Okay. Now the model will be again given each separately. So what it means is each process will run the whole model. The whole 1000 layers or however more layers, each model will run. Each process will run the model. And data will be split. How it will be split? So suppose there are 15 processes, the data will be split 100 by 15, correct? So in our case, somebody has 25 CPUs spread over 15 machines, the data will be split by 25, so 4 GB each. So what is happening? In both these architectures, I am cutting the data. So the amount of time taken to train will be less, or to fine tune will be less. So this is one kind of architecture. Both are similar if you see. One is just data parallel runs on one machine, multiple GPU. Distributed data parallel runs on multiple machines, multiple GPUs, right? Now, this is fine if your model is sensible. There is a possibility that your model is very big. If you are especially developing both the encoder, decoder, and there are a lot of classifier heads and lot of visual encoders, lot of other encoders are also running. Often you don't use a transformer by itself. You may be using a VLM. If you are using a VLM, what is there? There is also a vision level transformer. So the vision is running its own CNN and all that. So it's a massive setup. Some people have coupled GANs with LLMs. Some people have coupled a lot of other things with LLMs and run together. So what happens in that case is that the models become unwieldy and huge. In those cases, we cannot run the entire model on one machine in a single process, or even on one GPU. It won't fit in a GPU. See, a typical GPU has how much memory? It has 24 GB, or if you are using an A100, it has 40 GB. I have not seen general purpose GPUs available which are more than 40 GB or 60 GB. Max you will have 80 GB. So some models may fit in. There will be a considerable number of models which will not fit in this 80 GB at all. Then what do you do? So you can't use data parallel, you can't use distributed data parallel. Why? Because both of them need the whole model to run on the process on a single GPU. If the model cannot run on a single GPU because it's too big, the memory is required is too high, what do? Then you go for an architecture which we call model parallel. Model parallel means part of the model runs on one machine. Let's think about it. Suppose you have 1000 layers. I mean, let's make a dream of a network which is 1000 layers. You don't have to dream, there are really networks like that. So all 1000 layers will not fit on one GPU. What will you do? You will run 500 on one and 500 on another, correct? Now this is not as trivial as I am making it sound. What will happen? First, the data will pass through 500 forward pass. After forward pass, the 500 will go, output of the 500 will go and feed into the next 500. And it will go to the end, and then the loss will be known. The loss will be known on the second side, not on the first side, correct? And then the loss will have to be back propagated. That is not the problem. The problem is, while the second one is running, what should happen to the first one? Should the first one remain idle? No. Are you catching what I am saying? See, some batch of data was given. The first model ran on that data. The first part of the model ran on that data. Produced an output. That gave it to the second model, not second model. Second part of the model. Second part of the model is running on the second GPU. Yes? What happens to the first GPU? Does it remain idle? No. If it remains idle, then you are again losing performance, right? So, now something interesting happens. The first GPU runs the next batches 500 layers, but it doesn't know how to apply the gradient for the first 500. I don't know whether you're reaching me. I am reaching you. Are you getting the problem? See, my second part of the model is still running, and I have started with the next piece of data without knowing what is the gradient and what is the weight change I should apply. So what I have to do? I have to wait for the entire pipeline to clear. before I can apply weight change. Understanding? No. This is not easy. This is called pipelining. What is difficult to appreciate or the more nuanced part of this is, how do you back propagate the gradients while the other guy is still going on? Do it intelligently. So we'll talk about that. That's again a very intelligent process, and how do you do that? Because those are the real challenges. See, nobody will give you a model and say train. Life is not so simple. So these are the three possible scenarios. We talked about three scenarios. Data parallel, distributed data parallel, model parallel. In first two, data parallel and distributed data parallel, the whole model was running on one GPU. Many GPUs were there, many processes were there. Only in the model parallel architecture, we had the model getting split between GPUs, part of the one GPU running part of the model, another GPU running part of the model. And this situation becomes especially tricky where, imagine there are 15 machines, 15 GPUs, and can you imagine that hopping which is happening? No. So the 15th guy is doing the last part, the 14th guy is doing just the previous part, the 13th guy is one step earlier, all of them are waiting, all of them are hanging with, depending on where their position is, so many undone things which they have to redo. Okay. So anyway, we'll discuss that one day when you are probably more fresh and maybe more alert and more smart. I'll describe how pipelining happens. It's very interesting. Today, I'm going to talk about distributed data parallel or data parallel. Whatever I'm saying applies by and large similarly. Okay. Now let's talk about, is everybody clear what is distributed data parallel and data parallel? Yes? No? Okay. No, I think you will get this. So what is the challenge now? First, let's understand the challenge and then we'll see how to solve it. Now, just imagine in your mind, I can draw it, but I'm sure you can imagine also. Let's just imagine a very simple picture. Okay. Let's imagine 4 GPUs. Doesn't matter, they are all on one machine and or on different machines, it really doesn't matter. Okay. Can you imagine 4 GPUs, 4 processes, each having a model? Yes, each having those billions of parameters or millions of parameters or whatever. So there are 4 models getting fine-tuned, each running on a different GPU, each having its own parameters. First thing that happens is the way the data splits. So each guy is dealing with his or her own data or his data. Each GPU is dealing with its own data. So again the picture is 4 processes, 4 chunks of data for one for each process, each GPU or each process getting trained on one GPU running one training loop or multiple training loops. Now each training loop consists, now let's go deeper into the training loop and understand what happens in the training loop. So each training loop is what? Forward propagation happening on each with its own piece of data. Forward propagation happens and now that is easy. Forward propagation easy. Just apply weights and you get an output. You get Y pred. Y pred is easy. Y loss is also easy. I mean loss is computation, is cross entropy, MSE, whatever you do, you get some loss. Now what you have to do? You have to take the derivative of loss with respect to weight. That is also easy. You know the weights, so you know the loss, you apply chain rule, you get it. So you get a bunch of gradients. Now comes the punch. So each of these 4 guys, each of these 4 processes has computed their own gradients. Do you agree? Yes? Now, my simple first question is, are all the gradients, if you take one weight, let's say W1, is dou L by dou W1 same for all the 4? Yes, no, no. And why is it not same? I am sorry. Because they are dealing with different data, as simple as that, right? So, loss is determined by data, and therefore the gradient is also dependent on the data. And obviously, when 4 different processes have seen 4 different data, they are not seeing the same data, the data has been chunked. Each guy is seeing a different data. So, when each process is seeing different data, they are seeing different loss, and then we have dou L by dou W1 on the first machine, first process, different in each one. Agreed? Yeah. Okay. Now, if I take this dou L by dou W1, not only dou L by dou W1 is different, the beta 1, the momentum term, and also the decay term, they are also dependent on the kind of earlier gradient, which is also different. So, neither are the gradients same, nor are the optimizer terms same. We call it optimizer state. Neither are the gradients same, nor the optimizer state same for the same weight with respect to the loss on 4 different processes. Now, if you think forward, if I directly take these gradients and these optimizer terms and use them to change the weight on a particular process, what will happen? No, maybe I said it badly. What I am saying is, suppose I just follow the standard algorithm of back propagation, take the dou L by dou W1s, beta 1s and beta 2s of one process and use it to change the weight of that process or that copy of the model, what will happen? Did I make my question clear? Yes? What will happen? I'll end up having, if there are 4 processes involved, I'll end up having 4 different models. Agreed? No. Because what is a model? Basically the layers and the weights. Together they are called the model. Correct? So, I will have 4 different models. That is not my intention. That will screw up the whole thing. This is a different model. I don't know which model is better, which model is worse. That's not how it is to be done. Yes? So, if I leave things to themselves and just allow to train, on their own it's not going to happen. On their own they are going to become a mess, and I am going to have as many models as there are number of GPUs in the game. Correct? Now, does everybody buy this? What I just said, have you understood? Yes? If you don't understand, I don't mind elaborating. It's very simple. Each guy is looking at his own data, it's computing its own derivatives, and when it is computing its own derivatives, it has to take those derivatives beta 1, beta 2 and make the weight changes. If it has to make the weight changes, each guy makes his own weight change, each guy will be running to though they may have started with the same random weights initially, each guy will run to his own, march to his own drummer, because I am seeing different data, I will get trained differently. That's not what we want. We want one model to emerge at the end of fine tuning, not 15 different models or 14 different models. That's not what we were seeking. Correct? So, how do you make this picture whole? How do you consolidate this picture? Okay? So, that is where a very important part or algorithm comes in. That is what is the value of data parallel or distributed data parallel. That's the real value proposition, which PyTorch supports very nicely and very cutely. How does it do it? So, what it says is, let each process compute their gradients, but before the gradient is applied to the weight, don't allow blindly the gradient to apply to the weight. So, whenever the gradient is to be applied to the weight, let all the gradients go to a single node, which we call or designate as the master node. Let all the gradients flow to the master. What will the master do? The master will aggregate all the gradients, then average out all the gradients. Are you getting me? Then send this averaged gradient back to each guy and say, this is the gradient you go and apply. Made sense? So, though each guy is computing his own gradient, the gradient is not used as it is. The gradient is sent to a standard master, designated master. Master takes all the gradients, aggregates them, averages them, and sends it back. Now, this is nice to say. And after that, because it's the same gradient change, this is called, the process I have just mentioned, there are two names for it. The simple English name for it is called synchronization of gradients. The more sophisticated term for this is called all reduce. Take all and reduce it into one. So it's called all reduce. So that is a term we use for this is a very famous algorithm, very trivial algorithm if you will, and that is what is used. So that is a technical term. In short, it is doing synchronization between all the gradients, normalizing all of them, bringing them to a common level. So then what happens? Then once the gradient is same for with dl, dou L by dou W1 is same for everyone, then it is applied and the weight change. So all the models, though they train separately, because of the synchronization process, they are all following the same weight change. Because if weight change is same, the model is going to work the same way. It is not going to alter. So the trick is the weight update should be synchronized. That's the trick. So that is what they do. That's point number one. Now, this is a sunny day scenario, what I just described. Now, there is a danger here, or there is not so sunny scenario also here. What if one of the machine is, here we are assuming two things. A, all GPUs are up, one. Second, all GPUs are running at the same speed or by and large the same performance. By the time this guy has computed his gradient, he is also computed, that's why he is able to collect and apply. Now, this is not always true. All machines participating in the cluster may not be all equal. Some machines may be fast, some machines may have more memory, some may have faster GPUs. So it's very much possible that the gradient computation on one machine and the gradient computation on another machine may not be same, may not be happen at the same time. So what happens? Then you have a problem. What is the problem? You are dictated by the lowest, weakest link, like a relay. Like a relay race, whoever is the slowest, he will dictate the finish, right? So here also that is what happens. There is a delay there of whatever time, and so it happens. Yeah? So somebody has to wait. That is okay. What if somebody gets killed? Some GPU goes down. So out of 15 GPUs who started, it's waiting for aggregation of 15, only 14 arrive. What happens then? Okay. Then you have a loop, then you have a problem, then you have to have a protocol which will announce heartbeat, and it will say this heart is not beating, throw it out. Correct? But there will, time loss will be there. So all that is there. But assuming that all the machines are up, this is a pretty good and smart way of doing it. Okay? So this is what is called distributed data parallel. Very simple idea, very easy to follow. Yes? Okay. Now, what the PyTorch guys have done, I am now talking about the implementation. See, if you make the programmer do all this, that is, make the programmer implement all reuse and all reduce and all the thing which he has to take care when one of them is not working or whatever, one of them is slow. If you make the programmer do this, then the programmer will say, oh my God, and more on top of that, I am being made to do all this protocol and all that kind of stuff. It's too complex. I am not, I'll leave this part of computer science. See, I'll design a website. Okay. So you can do that. That's one option. But what they have done, the PyTorch guys have done, and this is remarkable from a software engineering aspect. What they have done is, I'll show the code also. They have created a beautiful wrapper. Now, those of you who go on to work in companies which are high-end, you will have to develop admiration for this kind of design. What they have done, they have said, give me the old model, the model which was designed for a single process, single GPU architecture, and I will provide a packager for that model, an encapsulator, if you will, for that model. This encapsulator is like a package or like a library around the original model. So you take the original model, we'll wrap that model with a packager and give you another model. In this model, when you say backpropagate loss, you'll say only one line, just like you say in a regular model. You just say backpropagate the loss dot back, correct? Or backward, whatever. You say the same thing. Only thing is, this is implemented on a model which is already encapsulated, which will do all this, what I have just explained. The all reduce, the starting up, the stopping, all of it will be done without the programmer having to lift his finger. Understanding? It's happening all behind the scene by just allowing your model to be wrapped inside this nice package, and the package will alienate or isolate the programmer from any of this complexity. I like that the most. That's the beauty of this PyTorch. They have completely alienated this skullduggery of doing this entire communication and all. There's a library used for this called NCCL, NCCL, which is NVIDIA Collective Communication Library or something like that, which is used internally for all this communication and all that. So that is what gets used. But you don't see it. The beauty is you never see it. You say what? Loss.propagate, optimizer.step, as if you are just doing a basic optimization. Now when you say optimizer.step, you know what is happening? It is getting all the gradient from the aggregator, getting it done, all the optimizer states it is getting from everywhere, and then applying the weight change. Now it is doing all this, but without your knowledge. I mean, you are obviously knowing it is happening, but you don't have to make any programming alteration to make this happen. This all happens behind the scene in the black box. And this, I would say, if somebody would give an award for elegance, I would say PyTorch definitely is a candidate, because the neatness with which it has been done, it's very simple. Just as if I am writing the same code. As if I am writing code for a single GPU, single process code, I write the code same way, but internally it is using the DDP. So that is the power of DDP, point number one. The second point is, okay, now going forward, I think before I show you the code, I will talk about a few more things, and then I'll show you the code. There is another mechanism which is at play here. See, on regular basis, what happens during any training process and which happens during fine training process? Often the training may get interrupted, correct? So what needs to happen during training? Snapshots have to be stored. So now, in this case, if you have to store the snapshot of weights, there is only one weights. The same weights are there, because the same weights are getting updated, right? So the snapshot is stored at, okay, yeah, maybe I should make it more clear. Imagine there is power outage, there is UPS gone, all the 15 processes have come down, okay? And just before coming down, let's say, the last snapshot was saved. Now, should the snapshot be saved in 15 places? No. The snapshot is saved at the master. And what happens when you come up is, it's this master which broadcasts again silently without you knowing, silently broadcasts all the snapshots to all the 15 machines, 14 machines, and says now you come up with that particular snapshot, happening completely transparently. So that's another thing which you have to keep in mind, that that the storing of the checkpoint, creation of the checkpoint, and more so the restoration from the checkpoint also happens in a distributed way without anybody caring or knowing about it. Okay, that's point number 2. The point number 3 and 4 are also, I wanted to touch upon, are important. I'll touch upon the point number 3 first. Of late, there have been changes to the fine tuning process also. The basic process is what I described, but of late there have been changes. One significant change which is conceptual and you need to understand is like this, okay, and you will have to think a little with me. Again, the change is called LoRa. Some of you must have heard of this word LoRa. What does LoRa stand for? Low rank adaptation. What does it mean? Okay, I'll describe it maybe for general use. LoRa is a technique of fine tuning. It's an alteration to the standard process of fine tuning. Okay, now you have to understand the justification for LoRa. See, why is parameters in billions? Because the weight matrices are very big. Why are the weight matrices very big? Because the neurons at every layer, or you can say especially in the fully connected layer of a transformer, the neurons are so many that because there are 4096 neurons or 8192 neurons, it's become big, it's become unwieldy. So because if you have lot of neurons, obviously the compute power which is required is more, and all of that. So the weight matrices which have to be multiplied are also more. It's directly proportional, isn't it? For example, if you just look at the fully connected block of a transformer, what is it doing? It is moving from one dimension, which nowadays for any transformer, what is the dimension? D. What is generally D for a transformer? Please take that paper and read it with ChatGPT. There are many people who have given good interpretations of it. One of them is me. You'll find my interpretation in that KMIT Vista, attention is all you need. I'm not saying it's the best interpretation by any way, but it's a good interpretation. Read it, understand it. One. Second is, there is, I don't know whether you know this writer, his name is J. Alamar. Have you heard of this? A-L-A-M-A-R, Alamar, J. Alamar. Very popular, is written very nicely about attention is all you need. It's a very fundamental paper. Read it and understand it. Maybe one day we'll have a lecture online probably, because unless you understand transformer, what will you do? You can't create an LLM. Here I am just talking about fine tuning an LLM, but understanding an LLM is also fundamental. Okay. Now I am going back a little. Okay. Now I am talking about a technique called LoRa. Okay, I'll try and make it in a very general way, or maybe I should not talk about it now. Okay, we'll delay this session. I'll stop here, because if you don't know transformer, I think you should know transformer. Let me pause a little. No point. You should first learn to walk before you run, correct? Agreed? No. Okay, we have just described DDP, we have described how it happens. I'll pause here. We'll resume maybe on Thursday, next Thursday. But there is a guarantee you should read LLM and come. Or rather read attention is all you need. You should read all of that. Okay, we'll stop.